With the name of Allah, the most merciful and beneficent. Assalamu alaikum. I am your instructor, Ms. Saida Sidra from Department of Chemistry. Today is our second lecture from Solids chapter. But before starting this lecture, first have an overlook at the topics which we have discussed in previous lecture. We have discussed in detail about the introduction of solids, kinetic molecular interpretation of solids, properties of solids, like for example we have discussed about the diffusion, expansion, compression, their motion, intermolecular forces. And the fourth topic which we have discussed about the types of solid. Mainly there are two types, crystalline and amorphous solids. We have discussed about their definition, examples, and also the differences between both these types of solids. And the last topic which we were discussing in the previous lecture, it's about the properties of crystalline solids. And almost all the properties we have discussed. We are left with one subtopic from this topic, allotropes of oxygen and sulfur. We have discussed in detail about their geometrical shape, melting point, symmetry, habit of a crystal, about allotropy, isomorphism, polymorphism. All these properties we have discussed. In today's lecture, the topics which we will cover, we will discuss first about the allotropes of oxygen and sulfur, and then crystal lattice. So starting with the allotropes of oxygen. First revise this allotropy. What is allotropy? It is the existence of an element in more than one form. Consider oxygen over here, means that we have this oxygen. So this oxygen, it can exist in more than one form. We have two allotropes of oxygen. We have dioxygen or trioxygen. This dioxygen is also called as what? Molecular oxygen, and this trioxygen is also called as ozone. And you are quite familiar with both these allotropes of oxygen. These allotropes, they are obtained by the absorption of heat from the atmosphere. This oxygen, it absorbs heat from the atmosphere and it is converted into the ozone. And delta H for this reaction we have, it's 142 kilojoule per mole. These are the structures of molecular oxygen. In this we have two oxygen atoms. They are bonded to each other. They are bonded to each other through double bond. And the composition of this double bond is what? One bond is sigma bond while the other bond is pi bond. While here in this ozone, we have three oxygen atoms. They are linked together, and the bond angle between these three oxygen atoms, we have 117 angstrom. 117 degree. It is the bond length between two oxygen atoms in ozone. It's 1.278 angstrom. Next we will discuss about that how these allotropes they are formed, means that how one allotrope is obtained from the other allotrope. The molecular oxygen, it absorbs the heat from the atmosphere and it is converted into this ozone. In what form of heat? It absorbs the ultraviolet radiations from the sun and it is converted into the ozone. The reaction is basically photochemical reaction. Photochemical means, photo means light. That this reaction, it is occurring in the presence of this UV light, and this O2 will be converted into O3. This conversion of this molecular oxygen into the ozone, it is spontaneous and one directional. So it is called as what? Monotropic. Monotropic means that moving in one direction. and the concentration of ozone we have, it's 10 parts per million. It occur at 24 to 30 kilometer from surface of Earth in stratosphere. It lies in the second layer of atmosphere, and its distance from the surface of Earth is about 24 to 30 kilometer. This is the concentration of ozone present in stratosphere. If the concentration of ozone is increased beyond certain limits, it is dangerous to the atmosphere. It has characteristic smell. It will be hazardous if its concentration exceeds 1000 parts per million. In this figure, it's also explained that how ozone it protects the earth. First step involves the absorption of light by oxygen molecule from the sun. Means oxygen molecules, they are photolyzed, which results in the formation of 2 oxygen atoms. Now these 2 oxygen atoms, they further interact with the oxygen molecule, and we will have the formation of this ozone. And ozone and oxygen atoms, they are continuously being interconverted as the solar UV breaks ozone and the oxygen atom reacts with another oxygen molecule. This reaction is a fast reaction, and this interconversion, it converts the UV light into thermal energy, which is responsible for heating the stratosphere. We are quite familiar with this thing, that ozone, it acts as a protective layer, means it protects the earth from the harmful radiations coming from the sun. But some of the ozone is lost by reaction of the oxygen atom or the ozone molecule with each other, or some other traces gases such as chlorine. That the destruction of ozone is taking place day by day due to different factors. So this figure, it graphically explains that how oxygen molecule is first converted into the ozone molecule. Next we will discuss about the allotropes of sulphur. We have 4 different allotropic forms of sulphur: rhombic sulphur, monoclinic sulphur, plastic sulphur, and amorphous sulphur. We will discuss these one by one. This rhombic sulphur, which is also called as alpha sulphur, it is having bright yellow color. It is crystalline in nature, and its crystals are basically rhombic octahedral crystals. It is stable below 96 degrees Celsius, and it is made up of S8 molecules. This figure is explaining the structure of rhombic sulphur. Just look at this structure, this crystal structure. It is the octahedral crystal of rhombic sulphur. And this figure, it gives you the explanation about the S8 molecule, the ring structure of S8 molecules. We have 1, 2, 3, 4, 5, 6, 7 and 8 sulfur atoms joined together. In rhombic sulphur, the crystal structure is what? Octahedral. They are stable below 96 degrees Celsius. They are crystalline in nature and having bright yellow color. The next allotrope of sulphur, we have monoclinic sulphur, which is also called as beta sulphur. It is also crystalline in nature, but its structure is different from the rhombic sulphur. Rhombic sulphur, they have octahedral crystals, while monoclinic sulphur, they have needle-like structure. And this monoclinic sulphur, it is stable between 96 degrees Celsius and 119 degrees Celsius. It is also converted to rhombic sulphur. This figure, it represents the structure of monoclinic sulphur. Just look at this. They are also having yellow color, but their appearance is different from the rhombic sulphur. That monoclinic sulphur is having needle-like structure. Both rhombic sulphur and monoclinic sulphur, they are interconverted between each other If we have rhombic sulfur, the octahedral crystal of rhombic sulfur, and temperature increases above 96 degrees Celsius, so it will be converted into monoclinic sulfur. But if temperature remains below 96 degrees Celsius, then monoclinic sulfur is converted into rhombic sulfur. The third allotrope of sulfur we have plastic sulfur or gamma sulfur. It is the supercooled form of sulfur. It is produced when the molten sulfur, when we heat the sulfur, it is converted into its molten state. When molten sulfur is rapidly poured into cold water, what happens? It will roll up and produce yellow ribbons of this plastic sulfur. It is not the true allotrope of sulfur. It is basically soft and elastic in nature, and it is insoluble in hydrogen sulfide. This is the structure of this plastic sulfur. Although it's not too much yellow, but its color is basically it's linked to this sulfur. The last form of sulfur, allotropic form of sulfur given in your book, it's amorphous sulfur. It is irregular crystalline shape. It is not found in free state. It is prepared by passing H2S gas through water for a long time. Then that saturated solution of H2S obtained is exposed to air. First, what you have to do, that you have to pass hydrogen sulfide gas through water for a long time. Then as a result of this, you will obtain saturated solution of this H2S, which will be exposed to air. It is almost having white color or very light yellow color. So all these are the four different allotropes of this sulfur: rhombic sulfur, monoclinic sulfur, plastic sulfur, and amorphous sulfur. Next topic we have crystal lattice. As we have discussed earlier, that in crystalline solids they have definite shape. But what factor is responsible for their definite shape? The regular arrangement of the particles in a crystalline solid is responsible for their definite shape. That it determines the shape of the crystals of crystalline solids. The arrangement of the particles of a crystalline solid, it determines the shape of a crystal. And the position of these particles in the crystalline solid is represented by a lattice. And what is this lattice? If we define the lattice, it is the systematic arrangement of atoms in a crystal is called as lattice. And this lattice, it determines the structure of any substance. It is systematic arrangement, not the irregular arrangement of the atoms. Due to this systematic arrangement of the atoms in a crystal, it determines the structure of that particular crystalline solid. It is of three types. It can be three-dimensional lattice, it can be two-dimensional lattice, or it can be one-dimensional lattice. We have defined this lattice. Now what is this crystal lattice? If we define the crystal lattice, it is an array of points representing the arrangement of the particles. What are these particles? The particles, they can be atoms, ions, or molecules in three-dimensional spaces is called as crystal lattice. An array means an arrangement of points. Points, we have discussed the lattice points representing the arrangement of the particles. How these particles, they are arranged in three-dimensional spaces is called as crystal lattice. The external conditions, the external shape of a crystal, it depends upon the conditions of crystallization, that under what conditions this crystallization process is taking place. If we change the condition, then the shape of a crystal, it can be changed from one form to another form. It will be different in some conditions, and then crystal shape, it can be changed in different conditions. We have discussed this also earlier in case of sodium chloride. Sodium chloride is cubic at ordinary conditions, but it will be octahedral in presence of urea. But internal structure, it remains the same with the basic structural unit. Means by changing the condition, the external shape of a crystal, it can be changed from this cubic to octahedral, but the unit cell basic structural unit, it will be remain same internally. Primarily, a crystal, it depends upon two things. It depends upon the shape of the unit cell and contents of the unit cell. Now we will discuss in detail about this unit cell, that what is unit cell. Unit cell is the smallest part of the crystal lattice, having all the characteristic features of the entire crystal is called as unit cell. This is the smallest part of the crystal lattice that has all the characteristic features of the entire crystal. This is the basic structural unit of the cell. It has different properties. That a unit cell, it shows the structural properties of a given crystal. When unit cell is repeated in 3 dimensions, it gives the entire crystal. And the complete information about a crystalline substance is present in a unit cell. It is the basic repeating unit of the crystal lattice. Just have a look at this figure. This is the cubic crystal lattice structure. This hole is representing the crystal lattice, and this is the small cube unit cell. And this is repeated again and again, which gives you this crystal lattice. And all these points, they are what? They are lattice points. We will discuss in detail about the structure or the shape of sodium chloride, and how different ions they are located in sodium chloride. That each sodium ion is surrounded by 6 chloride ions and vice versa. Means if each sodium ion is surrounded by 6 chloride ions, then each chloride ion is surrounded by 6 sodium ions. And the size of chloride ions is greater than sodium ion, because chloride ion, it has 18 electrons and sodium, it has 10 electrons. Now I will show you a video in which you will be able to understand that how in a cubic structure of this sodium chloride, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. Structure of sodium chloride. Sodium ions, they are smaller in size as compared to the chloride ions. If we calculate the radius ratio for both of these, then it comes out to be 0.5 to 6 radius ratio. And this radius ratio suggests that each sodium ion having grey color, they are surrounded by 6 chloride ions present in this cubic structure. Just have a look at this. Each sodium ion is surrounded by 6 chloride ion. And in the same way that each chloride ion is surrounded by 6 sodium ions in this crystal lattice structure. That each sodium ion is surrounded by 6 chloride ions having octahedral structure, and each chloride ion is surrounded by 6 sodium ions also giving the octahedral structure. We have seen in this video that each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions. Coordination number. What is coordination number? It is basically the number of negative ions which contact the unit positive ions. In sodium chloride, we have seen this thing, that each sodium ion is contacted with 6 chloride ions at the corners of the octahedron, so the coordination number of sodium will be 6. In similar way, the coordination number of chloride ion is also 6. Now we will discuss in detail about the number of sodium and chloride ions present in each unit cell of this sodium chloride structure. This sodium chloride is having cubic crystal. In a cube, it has 6 faces, 8 corners and 12 edges. What are the locations of sodium and chloride ions in a cube? Chloride ions, they are present at faces and corners, means they are present at 6 faces and 8 corners. While sodium ions, they are present at edges and center of the cube. Center means in the middle of that cube one sodium ion will be there. Just have a look at this structure. All these are the 8 corners of this cube. And we have 6 faces of this cube. And these are edges of the cube. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 edges, 8 corners and 6 faces present in a cube. And chloride ions in sodium chloride ions, they are present at the faces and corners, means at these 8 corners chloride ions they are present, and in these 6 faces they are also chloride ions. And sodium ions, they are present at these 12 edges and the center of this cube. Now we will calculate one by one that how many chloride ions and sodium ions they are present in each unit cell of a sodium chloride, and I will explain this with the help of a video. First we will discuss about the calculation of chloride ions and sodium chloride, and we said this thing that the chloride ions, they are present at the 8 corners of this unit cell. If you draw the chloride ions in this way, and each chloride ion is shared among 8 unit cells present at the corners. So we have 8 corners in a cube, and each chloride ion is shared among 8 unit cells. So we remove the part, we just represent that part which is shared by 1 unit cell. Means that 1/8th part of this chloride ion is present at each corner of unit cell. First we will calculate the chloride ions at the corners and then the faces. We have drawn the chloride ions present at the corners. Now we will draw the chloride ions present at the faces. We have 6 faces, so 6 chloride ions will be present at 6 faces of this unit cell. One over here, one at this side, one at this face, one at this, one at this top one, and one at the back, which I have shown in this dotted way. So 6 chloride ions will be present at these 6 faces, but each face of this unit cell, it is shared among 2 unit cells. And first calculating about the chloride ions present at the corners, if I fill up the shade present at each corner of this cube, so the 1 chloride ion present at the corner, each corner it will be 1/8th of 1 chloride ion, means that 1/8th of chloride ion is present at each corner. So in order to calculate the total number of chloride ions present at the 8th corner, we will have this 1/8. So this 1/8 is multiplied by 8 corners. 8 will be cancelled out with the 8 and we are left with 1 chloride ion. So overall, all the chloride parts present at the 8 corners, it will compose 1 chloride ions. Now we will discuss in detail about the number of number of chloride ions present at the faces. We have 6 faces. So each face of this unit cell, it is shared among 2 unit cells. If we draw a line, it will be like this, that half of the chloride ion it is present in one unit cell and half of the chloride ion it is present in the other unit cell. Means that it is 1 by 2. It is 1 by 2 part of each chloride ion. Now if we calculate that how many total chloride ions present at the faces, so we will have that it will be 1 by 2 multiplied by 6 faces. So the overall chloride ions we will get 3 chloride ions. They are present at 6 faces. We have 3 chloride ions at 6 faces and we have 1 chloride ion present at corners. So the total number of chloride ions present in one unit cell, we have 4 chloride ions present in one unit cell. Now we will calculate that how many sodium ions they are present in one unit cell. And we have discussed this thing that the sodium ions they are present at the center. One sodium ion it is present at the center of this cube, while the other sodium ions they are present at the edges. And this one big one is the sodium ion which is present at the center of this cube. Now I will draw the other sodium ions present at these edges. We have 12 edges in a cube, and each edge is shared among 4 unit cells. Means that the part of the sodium ion present at each edge, it is 1 by 4th part. So we can calculate the sodium ions in this way. We have 12 edges. I have drawn all the sodium ions present at the edges, and one is present at the center of this cube unit cell. We have 12 edges. So first we will calculate the total number of sodium ions present at the edges. We have 12 edges, and each sodium ion, I will repeat this again, that each sodium ion present at the edge, it is shared among 4 unit cells. So it will be 1 by 4th part of each sodium ion. So I will show only that part which is present in one unit cell. So it will be 1 by 4 multiplied by 12. If we calculate the sodium ions, so this 12 will be cancelled out with this 4, and we have 3 sodium ions present at the edges. So the total number of sodium ions present at all these 12 edges in a single unit cell, we have 3 sodium ions. And we have one more sodium ion which is present at the center of this cube. It will be written as it, means that the body of this cube, it contains how many sodium ions? 1 sodium ion. So total number of sodium ions, we have 3 sodium ions plus 1 sodium ion, we have 4 sodium ions. So in this way, that the total number of sodium and chloride ions present in a single unit cell, we have 4 chloride ions and 4 sodium ions. So if we combine both of this, we will get 4 sodium chloride. As we have seen in this video that we have calculated chloride ions and sodium ions. The total number of chloride ions present in each unit cell, we have 4 chloride ions, and the total number of sodium ions present in each unit cell, we have 4 sodium ions. So 4 NaCl can be written. The next topic for the solids, we have types of packing arrangements in solids. That packing of atoms present in the metal, it describes its structure, that how the atoms, they are packed together in a metal. And the atoms in a metal, they are considered to be spheres of identical size. We have two types of packings. We have an open packing and closed packing. Among both of these packing, the closed packing is the most efficient type of packing arrangement. And in this closed packing is the most efficient arrangement of the spheres, and in this closed packing, each sphere, it touches 6 neighboring spheres. Now have a look at this figure, so it will be clear to all of you that what is difference between an open packing and closed packing. This is the open packing arrangement, and this is the closed packing arrangement. And in this open packing, if we have this layer of sphere and we want to place the second layer of these spheres, so they are just placed above the spheres of the first layer, and each sphere is further linked with the 4 spheres, having lot of spaces between them. While in closed packing, if we have single layer and if we want to place the second layer, so what happens, they are placed in such a way, they are placed in the spaces created by the first layer, so having less spaces, and in this each sphere it touches the 6 neighboring spheres. So the closed packing will be the most efficient arrangement of the spheres. In closed packing, further we have different arrangements. If we want to place the second layer of spheres above the first layer, so each layer will be added in a space created by the first layer. Means that this void is void. What is the meaning of this void? That the space created with this void is what? Void is the space. Okay, so the second layer will be placed above the first layer in the voids created by the first layer. Spheres of the second layer will produce 2 types of voids. So after placing the layer B on layer A, it will again results in formation of 2 types of spaces or holes. We have tetrahedral holes and we have an octahedral hole. If you look at the placement of the second layer from the top, you will observe 2 types of holes. Tetrahedral holes, these they fall above a sphere in the first layer or bottom layer, and the octahedral holes, they fall above a space or void in the bottom or first layer. So next, in the closed packing, if we want to place a third layer on the second layer, we will have 2 types of possibilities. That in adding a third layer of spheres, there are 2 possibilities. We have hexagonal closed packing and cubic closed packing. What is the difference between both of these? If tetrahedral holes, which are created by the placement of layer B on layer A, if tetrahedral holes they are covered, then the third layer is identical to the bottom layer. Okay, this pattern is called as, and it is written as AB type of packing or 1-2-1-2 type of packing. While in cubic closed packing, this, if octahedral holes they are covered, both the tetrahedral holes and octahedral holes, they are created by the placement of layer B on layer A. If octahedral holes they are covered, then the third layer is not identical with the bottom layer. Means third layer is different from the first layer. Here in hexagonal closed packing, the third layer is similar to the first layer. It is usually written as ABC type of packing or 1-2-3-1-2-3 type of packing arrangements. So these are 2 types of closed packing: hexagonal closed packing, and we also call it as HCP packing, and cubic closed packing, we also call it as CCP packing. AB or 1-2-1-2 type of packing, ABC or 1-2-3-1-2-3 type of packing. Have a look at this figure. we have this A layer. We want to place the B layer, and this B layer is placed above the voids or the holes present in the first layer. This is AB layer. Now placing the third layer. In this we have both the tetrahedral holes and octahedral holes. If the tetrahedral holes, they are covered present in this AB layer, so we will have AB type of packing or AB stacking sequence, which is also called as hexagonal close packing. While if octahedral holes present in these layers, they are occupied by the third layer, then we will have ABC type of packing or ABC stacking sequence. This is also called as cubic close packing. So these are the different packing arrangements in the solid. That's all about today's lecture, and we will cover rest of the chapter in next lecture inshallah. Allah Hafiz.